There is an object drifting silently through the outer darkness of our solar system, billions of kilometers from the nearest source of warmth, spinning slowly in the frozen void, and we have never sent a single spacecraft to study it up close. We have passed it. We have glimpsed it from a distance. We have even recorded data about it as we flew by at extraordinary speed. But we have never stopped. We have never looked back. We have never tried again. And the reason why is one of the most fascinating stories in the entire history of space exploration. If you find this kind of thing as mind-bending as we do, stick around and subscribe, because this is exactly the kind of mystery we dig into here. The questions that don't have easy answers, the corners of the universe that most people never even think to look at. So let's start at the very beginning, because to understand why no probe has ever been sent to the specific object we're talking about, you first need to understand what it is, where it lives, and why getting there is one of the hardest engineering challenges our civilization has ever faced. And then we can get into the truly strange part of the story, the politics, the timing, the science, the extraordinary cosmic coincidence that brought one lonely spacecraft close enough to photograph this thing in the first place. This is the story of a world at the edge of everything, and it's a story that reveals something uncomfortable about how we explore space. Let's go back to 1989. The year is important because of what was happening in the solar system at that particular moment in time. Voyager 2 had been traveling through space for 12 years by this point. 12 years of uninterrupted flight through the void. A spacecraft that launched in 1977 and had already performed one of the most extraordinary journeys in human history. It had passed Jupiter in 1979. It had swung around Saturn in 1981. It had visited Uranus in 1986. And now in 1989, it was approaching Neptune, the eighth and outermost planet in our solar system. Voyager 2 is the only spacecraft in history to have visited Neptune. Think about that for a moment. We have sent dozens of missions to the moon. We have littered Mars with rovers and landers. We have orbiters circling Venus and Mercury and even the asteroid belt. But Neptune, the eighth planet, has been visited exactly once, by one spacecraft, more than 3 decades ago, and we have sent nothing since. After the Neptune flyby, something remarkable happened. As Voyager 2 continued its trajectory out of the solar system, it passed through a region of space that scientists were just beginning to properly understand. This region is called the Kuiper belt, and one of the first known objects in this belt sat directly in the spacecraft's path. The object is called 1992 QB1. Except that's not what people were calling it in 1989. Because in 1989, nobody knew it existed. The Kuiper belt itself was barely more than a theoretical concept at that point. The region had been predicted, hypothesized, discussed in academic papers, but it had not yet been formally confirmed through direct observation. That confirmation would come in 1992, which is actually where 1992 QB1 gets its name from. It was the first Kuiper belt object ever officially discovered, and it was found 3 years after Voyager 2 had already flown through the neighborhood. This is the object we are talking about today. And no probe has ever been sent to it, and the reasons why are more complicated, more human, and more scientifically interesting than you might expect. First, let's talk about what the Kuiper belt actually is, because most people have a vague sense of it without really understanding the full picture. The Kuiper belt is a ring of frozen debris that extends from the orbit of Neptune at roughly 30 astronomical units from the Sun all the way out to about 50 astronomical units. An astronomical unit is the average distance between the Earth and the Sun, which is about 150 million kilometers. So we are talking about a region of space that begins 4.5 billion kilometers from the Sun and extends out to about 7.5 billion kilometers. It's a vast, cold, dark ring of material left over from the formation of the solar system, a graveyard of ancient ice and rock that never got the chance to become a planet. Now, when people think about this region, they often think about Pluto, and that makes sense because Pluto is the most famous Kuiper belt object. It was the first one we ever visited with a spacecraft when New Horizons flew past in 2015. But Pluto is enormous by Kuiper belt standards. It's around 2,377 kilometers in diameter. It's big enough to have moons. It's big enough to have an atmosphere. It's big enough to have generated its own internal heat in the past. 1992 QB1 is nothing like Pluto. It's estimated to be somewhere between 150 and 200 kilometers across. Not tiny by any means, but nowhere near the scale of Pluto. It's a small, frozen, reddish world sitting quietly in the dark, doing what Kuiper belt objects do, which is essentially nothing. Orbiting the Sun once every 289 years or so, receiving almost no light, generating almost no heat, experiencing almost nothing, just existing. And yet, it matters enormously. Because 1992 QB1 was not just the first Kuiper belt object discovered, it was the proof of concept. It was the object that confirmed the Kuiper belt was real. Before 1992 QB1, scientists believed in the Kuiper belt the same way you might believe in a place you've never visited because someone you trust told you about it. After 1992 QB1, they knew. The discovery was made by astronomers David Jewett and Jane Liu, working with a telescope in Hawaii. They had spent years systematically scanning the outer solar system looking for slow-moving objects that might be hiding beyond Neptune. Most people had given up on this idea. Most people thought that if there was anything out there, we would have found it already. Jewett and Liu disagreed, and in August 1992 they found it. A tiny, faint dot moving against the background of stars, moving slowly, moving in the way that something very far away and very large moves when you're watching from a distance. The discovery sent shockwaves through the scientific community, not because 1992 QB1 itself was spectacular. It wasn't. It's a small, dark, cold rock. But because of what it implied. If this one object was out there, then there had to be more, many more. And the floodgates opened. Since 1992, we have cataloged over 2,000 known Kuiper belt objects, with estimates suggesting there could be hundreds of thousands of them larger than 100 kilometers in diameter. The Kuiper belt turned out to be one of the most populated regions in the solar system, an entire hidden world that we had sailed past without even knowing it was there. And Voyager 2 had passed right through it. Now here's where the story gets genuinely strange. When scientists went back and looked at Voyager 2's trajectory after the Kuiper belt was confirmed, they found something interesting. The spacecraft had passed relatively close, in cosmic terms, to 1992 QB1. Not close enough to image it, not close enough to study it, but closer than any other human-made object had ever come to a confirmed Kuiper belt object at that point. Voyager 2 had unknowingly brushed past the edge of a world we didn't even know existed. So why didn't we send another spacecraft to have a proper look? This is where the conversation gets complicated, because the answer is not one single thing. It's a whole constellation of factors, each one individually understandable, but together forming a wall that has kept 1992 QB1 in permanent isolation from human investigation. Let's work through them one by one. The first and most obvious problem is distance. Pure, brutal, unforgiving distance. 1992 QB1 sits at roughly 41 to 44 astronomical units from the Sun, depending on where it is in its orbit. That's somewhere around 6 to 6.5 billion kilometers away. To put that in terms that feel real, if you could drive to 1992 QB1 at highway speeds without stopping, the journey would take somewhere around 7,000 years. Even light, the fastest thing in the universe, takes more than 6 hours to make the trip one way. Now, spacecraft obviously travel much faster than cars, but even the fastest spacecraft we have ever launched, New Horizons, which holds the record for the fastest Earth departure speed of any probe, travels at about 50,000 kilometers per hour. At that speed, the trip to 1992 QB1 would take roughly 14 to 16 years, depending on the trajectory you take and the gravitational assists you can arrange along the way. 14 to 16 years is a very long time. It's longer than most politicians stay in power. It's longer than many careers. It's longer than some entire space programs have been running. And that's before you account for the planning, development, and launch phases, which for a mission of this complexity would themselves take another 10 to 15 years. So you're looking at a program that, from initial concept to first data return, could easily span 3 decades. That's not impossible. That's how long it took to plan and execute the New Horizons mission to Pluto. But it requires an extraordinary level of institutional commitment and patience, and those things are much harder to come by than rocket fuel. The second problem is scientific priority. And this one is harder to talk about because it requires being honest about the uncomfortable economics of space exploration. There is a finite amount of money available for planetary science missions, a finite number of launch windows, a finite number of engineering teams capable of building deep space probes. And the competition for those resources is fierce. Every mission to space is competing against every other mission to space for the same pool of funding and talent. When scientists sit down to argue about where to send the next great probe, they have to make a case. They have to explain why their target matters more than someone else's target. And this is where 1992 QB1 runs into trouble. Because while it's historically important, the object itself is scientifically generic by Kuiper belt standards. It's a cold, classical Kuiper belt object, which is a designation that refers to its orbital characteristics. It orbits in a near-circular path, relatively undisturbed, relatively unchanged from the early solar system. That makes it scientifically valuable in a general sense, but it doesn't make it uniquely compelling in the way that, say, an active comet, or an ocean-bearing moon, or a geologically active world would be. Compare it to other Kuiper belt objects that have generated more scientific excitement. Objects like Eris, which is actually larger than Pluto and helped trigger the reclassification of Pluto as a dwarf planet, or Makemake, which has a moon and an intriguing atmosphere, or Arrokoth, the target of New Horizons' extended mission after Pluto, which had never been disturbed by close encounters with other planets and represented one of the most pristine objects in the solar system. These are compelling targets. They have stories to tell that you can't tell in any other way. 1992 QB1 has a story too. Its story is the story of the Kuiper belt itself. It was the first. It proved the belt was real. It opened up an entirely new chapter in our understanding of the solar system. But that story has already been told, in a sense. The discovery happened. The confirmation happened. The revolution in thinking happened. And since then, every new Kuiper belt object discovery has added to the picture, not replaced it. The scientific urgency that 1992 QB1 might have generated in 1992 has been somewhat diluted by the sheer number of objects we've found since. The third problem is that we don't have the right spacecraft for the job. And this is not just a budget problem, it's a genuine engineering challenge that doesn't have an obvious solution. Sending a probe to a Kuiper belt object is extraordinarily difficult. The target is tiny, dark, and billions of kilometers away. By the time you get there, you have very little fuel left for maneuvering. You can't just hit the brakes and park in orbit, because the fuel required to decelerate at that distance would be prohibitive with current technology, which means any flyby mission gives you only a brief window to collect data, a window that might be measured in hours rather than days or weeks. New Horizons' flyby of Pluto lasted only a few hours at closest approach. The flyby of Arrokoth was even quicker. These missions are extraordinary achievements, but they are fundamentally limited by the physics of how we get from here to there. To actually orbit a Kuiper belt object, to stay with it, and study it over time, you would need a form of propulsion that we do not currently have operational for deep space missions. Ion engines can theoretically do it, but the journey time would be even longer, and the power requirements at that distance from the sun, where solar panels barely function, add another layer of complexity. This is a solvable problem in principle. Nuclear electric propulsion, or advanced solar electric propulsion, could get us there with orbital capability eventually. NASA and other agencies have been developing these technologies for decades, but developing them to the point where they're reliable enough for a flagship science mission, certifying them for flight, integrating them with a spacecraft that can survive a decade and a half of interplanetary travel, and then actually executing the mission, that's a process that takes enormous resources and time. The fourth problem is one that nobody likes to talk about, but which drives everything else: the political reality of long-term scientific funding. A mission to 1992 QB1 would require sustained commitment across multiple administrations, multiple Congresses, multiple changes of leadership at the relevant space agencies. History shows that this kind of sustained commitment is genuinely hard to maintain. Projects get canceled, priorities shift, New administrations come in and decide that their money is better spent elsewhere, and the further away your target is, the more vulnerable your mission is to this kind of institutional discontinuity. The New Horizons mission nearly died several times before it launched. It survived only because of extraordinary advocacy from the scientific community and a very specific political window that allowed it to move forward. The James Webb Space Telescope was canceled and revived and over budget and over schedule for so long that it became a kind of running joke in the astronomy world before finally launching and becoming one of the most productive scientific instruments in history. These things are hard to keep alive. A mission specifically to 1992 QB1 would be an even tougher sell than New Horizons, because at least Pluto had cultural resonance. People knew what Pluto was. People cared about Pluto. People got angry when Pluto was demoted from planet status. That emotional connection drove public support, which drove congressional interest, which ultimately kept the mission alive. 1992 QB1 does not have that cultural resonance. Most people have never heard of it. It doesn't have a name, even, which is its own fascinating side note. Let's talk about that for a moment. 1992 QB1 has never been given a formal name. Its designation is purely technical, a label assigned by the Minor Planet Center based on the year it was discovered and the sequence of its discovery within that year's survey period. Officially, it's now catalogued as 15760 Albion, a name that was given relatively recently, years after its discovery, but for a long time it was known informally as QB1, and the class of objects it belongs to, the cold classical Kuiper belt objects, were actually nicknamed Cubewanos, a phonetic rendering of QB1. The first member of its class left such a mark on astronomy that an entire category of objects was named in its honor, albeit informally. And yet the object itself remained nameless for decades. This is actually part of a broader pattern with outer solar system objects. They tend to get lost in the crowd. There are so many of them, and they are so far away and so difficult to study, that naming them takes a back seat to simply cataloging their existence. The Kuiper belt has changed our understanding of the solar system profoundly, but it has not captured the public imagination the way that the planets have. And that matters, because public imagination is ultimately what drives the political will to fund space missions. Now let's take a step back and look at this from a different angle, because there's another aspect to this story that's worth exploring in depth. What would we actually learn if we did send a probe to 1992 QB1? What's the scientific case for going? The answer turns out to be genuinely fascinating, because objects like 1992 QB1 are time capsules. They are preserved remnants of the original solar system, material that has been sitting in the deep freeze of the outer solar system for 4.5 billion years without being significantly disturbed. On Earth, everything is constantly being recycled. Rock gets subducted into the mantle and remixed. Water dissolves and erodes. Biological processes transform matter over and over again. Even on Mars and the Moon, volcanic activity and impact cratering have reworked the surface material repeatedly. But in the Kuiper belt, sitting at temperatures close to absolute zero, things stay the same. The chemistry that was frozen in at the beginning of the solar system is still there, waiting to be read. When we study Kuiper belt objects, we are studying the raw ingredients of the solar system. We are looking at the stuff that eventually got mixed together to build the planets, the moons, the asteroids, and ultimately the conditions that allowed life to emerge on Earth. The composition of these objects tells us about the chemical environment of the early solar system. The ratios of different elements and compounds can help us understand where they formed, how they migrated, and how the structure of the solar system evolved over billions of years. 1992 QB1 in particular is interesting because of its orbital characteristics. It belongs to a subgroup called the cold classical Kuiper belt objects, and cold here doesn't mean temperature, it means orbital eccentricity. Cold classical objects have nearly circular orbits with low inclinations, meaning they orbit close to the plane of the solar system and don't deviate much from that path. This is interpreted as a sign that they have never been significantly perturbed by gravitational interactions with the giant planets. They have been sitting quietly in the same general neighborhood since the solar system formed. Contrast this with hot classical Kuiper belt objects, which have more elliptical and inclined orbits, suggesting they have been scattered and stirred up by gravitational encounters with Neptune and the other outer planets. Or with the scattered disk objects, which have even more extreme orbits and are thought to have been flung outward from the inner solar system by close encounters with Neptune. Each population tells a different part of the story of how the solar system evolved. And the cold classical objects like 1992 QB1 tell the story of the earliest, most undisturbed part of that history. If we sent a probe to 1992 QB1 and could measure its composition directly, we would get an unprecedented look at what the outer solar system was made of before Neptune and Uranus started reshaping everything. We could measure the ratio of different ices: water ice, methane ice, nitrogen ice, carbon monoxide ice, and compare them to predictions made by models of the early solar system's chemistry. We could look at the surface for signs of space weathering, the slow transformation of surface material by cosmic radiation, and the solar wind, and use that to understand how long the object has been in its current form. We could look for binary companions, smaller objects that might be gravitationally bound to 1992 QB1, which would tell us about how these objects form and how their initial spin and shape were set in the early solar system. Arakoth, the target of New Horizons' extended mission, taught us an enormous amount along exactly these lines. Its distinctive contact binary shape, two lobes gently merged together, told us that Kuiper belt objects can form through a process called pebble cloud collapse, where small particles gently drift together under their own gravity rather than colliding violently. This was a fundamental discovery about how the building blocks of the solar system are assembled. 1992 QB1 could hold similar surprises. And there's another reason to go that has less to do with chemistry and more to do with structure. The Kuiper belt is not just a random scattering of objects. It has internal structure, gaps and concentrations that reflect the gravitational influence of Neptune over billions of years. The positions and orbits of individual Kuiper belt objects encode information about the history of Neptune's own orbit, and through that, about the dynamical history of all four giant planets. The NICE model, a theoretical framework developed in the early 2000s, proposes that the giant planets underwent a period of dramatic migration in the early solar system, with Jupiter and Saturn interacting gravitationally in a way that flung Uranus and Neptune outward to their current positions. This migration would have sculpted the Kuiper belt, creating the patterns we see today. Studying cold classical objects like 1992 QB1 in detail helps us test these models. Because if the models are right, the composition and structure of cold classical objects should reflect specific conditions that existed in the outer solar system before Neptune migrated outward. If we find something that doesn't fit, we need to revise our understanding of how the entire solar system was put together. This is not a small thing. The dynamical history of the outer solar system has direct implications for the delivery of water and organic materials to the early Earth. The bombardment of the inner solar system by comets and Kuiper belt objects in the early days is thought to be one of the ways that our planet acquired the water in its oceans, and potentially some of the organic chemistry that preceded life. Understanding where those impactors came from, what they were made of, and how they got on the trajectories that brought them inward is ultimately a question about our own origins. So the science is there. The value of a mission to 1992 QB1 is real and substantial. What's missing is the will and the resources to make it happen. Let's talk about what it would actually take to send a probe there, because I think walking through the specifics helps illustrate why this is so difficult in practice. The first thing you need is a launch window. The solar system is not static. The planets and other bodies are constantly moving, and the geometry of the solar system changes continuously. For a mission to a specific target in the Kuiper belt, you need to pick a launch date that puts your spacecraft on an efficient trajectory toward that target, ideally using gravitational assists from Jupiter and sometimes Saturn or Uranus to get a free boost in speed without burning enormous amounts of fuel. These windows open and close over years and decades. Miss one, and you might be waiting another decade for the geometry to line up again. New Horizons launched in 2006, partly because that was one of the best available windows for a Jupiter gravity assist that could then slingshot the probe toward Pluto in time to study it while Pluto still had an atmosphere. Pluto's atmosphere was predicted to freeze out and collapse as the planet moved further from the Sun, and scientists wanted to get there while it was still active. That kind of scientific urgency helped justify the timing. 1992 QB1 doesn't have an atmosphere that's going anywhere, so the urgency is lower, but the launch windows still matter enormously for fuel efficiency and travel time. The second thing you need is a spacecraft. And building a spacecraft for the outer solar system is not like building one for Mars. The challenges multiply with distance. Power is a major issue. At 40 astronomical units from the Sun, solar panels receive only about 0.06% of the energy they would receive at Earth's distance. That's not a typo. Less than 0.1%. Solar panels simply don't work out there. You need nuclear power, in the form of radioisotope thermoelectric generators, or RTGs, which generate electricity from the heat of radioactive decay. These are expensive, technically complex, and require careful regulatory approval because of the radioactive materials involved. The U.S. supply of the specific isotope used in deep space RTGs, plutonium-238, has historically been very limited. There have been periods where the U.S. had to restart production because stockpiles were running out. Beyond power, you need communication systems capable of transmitting data across billions of kilometers. At 40 AU, radio signals travel for more than 6 hours each way, so there is no possibility of real-time control. The spacecraft has to operate autonomously, following pre-programmed sequences and making its own decisions in the event of unexpected situations. The data transmission rate at that distance, even with the most powerful antennas, is extremely low. New Horizons transmitted data from Pluto at a rate of about 1 to 4 kilobits per second, which is slower than dial-up internet from the 1990s. Downloading all the science data from the Pluto flyby took 18 months. A mission to 1992 QB1 would face similar constraints. Then there's the question of what instruments to include. Every kilogram of instrument mass has to be justified against the fuel cost of carrying it. You want to bring cameras, obviously, spectrometers, to analyze surface composition, instruments to measure the particle environment and dust density in the Kuiper belt, possibly a radio science experiment to study the gravity field of the object, magnetometers, temperature sensors. Each instrument adds mass, adds power consumption, adds complexity, and the whole system has to survive a decade and a half of deep space, with temperatures swinging from the heat of the inner solar system during launch to the deep cold of the outer reaches, bombarded by cosmic radiation, with no possibility of repair if anything goes wrong. This is not an impossible engineering problem. We have done it before, with Voyager and with New Horizons and with Cassini at Saturn, but it requires expertise, commitment, and money. And in a world of competing scientific priorities and finite budgets, those resources flow toward targets that offer the best combination of scientific return, cultural resonance, and political feasibility. There's a growing scientific consensus that the Kuiper belt as a whole deserves a dedicated orbiter mission, a spacecraft that would not just fly past one object, but would maneuver through the region, visiting multiple targets over time. Such a mission has been discussed in the planetary science community for years. The 2023-2032 Planetary Science and Astrobiology Decadal Survey, the document that sets priorities for NASA's planetary science program for the coming decade, included discussion of outer solar system exploration. The top priority missions identified were focused on Uranus and a return to Enceladus, the moon of Saturn that jets water into space. A dedicated Kuiper belt mission was identified as a long-term goal, but not an immediate priority. This is not because scientists don't care about the Kuiper belt. Many of them are passionately invested in exploring it further, but the decadal process requires making hard choices, and Uranus has been waiting even longer than the Kuiper belt for a dedicated mission. The last time a spacecraft visited Uranus was Voyager 2 in 1986, and Saturn's moon Enceladus, with its subsurface ocean and active geyser plumes, represents one of the best candidates for extraterrestrial life in the solar system. These are compelling reasons to prioritize those targets first. But the conversation is evolving. As our knowledge of the Kuiper belt has deepened, as the scientific case for exploring these pristine remnants of the early solar system has become more clearly articulated, and as our engineering capabilities have improved, the prospect of a dedicated Kuiper Belt mission has become more realistic. Several mission concepts have been proposed and studied, including a concept sometimes referred to as a Kuiper Belt Explorer that would combine a flyby of one or more Kuiper Belt objects with a longer cruise phase studying the environment of the belt itself. None of these concepts has been formally approved and funded as of now, but the seeds of such a mission are being planted in the scientific literature and in the back rooms of the conferences where planetary scientists argue about the future of their field. And it's not impossible to imagine that within the next 2 or 3 decades, a probe could be designed, built, launched, and sent on a trajectory that takes it through the Kuiper Belt and close to targets like 1992 QB1. In the meantime, we have the data from Voyager 2's passage. And this is worth discussing in more detail, because people sometimes assume that the flyby, even at a distance, gave us significant information about 1992 QB1. It didn't, and the reason is the timing. Voyager 2 passed through the region where 1992 QB1 is located in 1989. The object was discovered in 1992, so when Voyager 2 flew past, nobody was looking for 1992 QB1 because nobody knew it existed. The spacecraft's instruments were not aimed at it. Its cameras were not targeted on it. It was not a known quantity. It was just empty space, as far as the mission planners were concerned. After the discovery in 1992, scientists went back and looked at Voyager 2's trajectory to see how close it had come to 1992 QB1's position at that time, and the answer was that it had passed in the general neighborhood, but not close enough, and not with instruments pointing in the right direction, to have gathered any meaningful data. The closest approach was close only in the context of the vastness of the Kuiper Belt. In absolute terms, it was still tens of millions of kilometers, which is close enough to confirm that the spacecraft and the object occupied the same general region of the solar system, but not close enough to do any meaningful science. This is one of the great cosmic almost moments in the history of exploration. If we had known about 1992 QB1 in 1977, when Voyager 2 was being designed and launched, we could theoretically have planned the mission differently. We could have added instruments specifically designed for Kuiper Belt observations. We could have adjusted the trajectory to bring the spacecraft closer. We could have had the cameras pointing in the right direction at the right time. We could have captured images and spectra and maybe even detected the object's surface chemistry. But we didn't know. We couldn't know. The discovery of the Kuiper Belt as a populated region of the solar system required advances in telescope technology and survey techniques that simply didn't exist in the late 1970s. It's a reminder of how profoundly our understanding of the solar system has changed just in the last few decades. When Voyager 2 launched in 1977, the Kuiper Belt was a theoretical concept with essentially no observational support. By the time it completed its tour of the outer planets in 1989, the Kuiper Belt was about to be confirmed. By the time New Horizons flew past Pluto in 2015, we had cataloged thousands of objects in the belt and built detailed models of its structure and history. The rate of discovery has been extraordinary, and it raises the question of what else we might be missing. What other populated regions of the solar system are sitting just beyond our current observational capabilities, waiting to be revealed? There is, actually, tantalizing evidence for exactly this. The existence of a hypothetical massive planet in the outer solar system, sometimes called Planet 9, has been suggested based on statistical anomalies in the orbits of certain distant Kuiper Belt objects. These objects appear to have their orbits clustered in a way that would be very unlikely if the outer solar system were gravitationally smooth. The most natural explanation is that something large is out there, pulling on these objects and organizing their orbits. If Planet 9 exists, it would be roughly the size of Neptune and would orbit at several hundred astronomical units from the Sun, far beyond the Kuiper Belt. We have not found it yet, but the search is ongoing. The history of planetary discovery in our solar system has a consistent pattern. We find something unexpected, we build better tools to investigate it, we find more things we didn't expect, and our model of the solar system gets more complex and more interesting with each iteration. The Kuiper Belt followed this pattern exactly. The discovery of 1992 QB1 opened a door that nobody realized was there, and 3 decades later we are still mapping what lies behind it. 1992 QB1 itself, sitting quietly at 44 astronomical units, spinning in the dark, will still be there waiting when we finally do get around to visiting. Its orbital period is almost 300 years. It moves so slowly that human civilization will change enormously before it completes another full orbit of the Sun. But the object itself will not change in any meaningful way. It has been in the deep freeze for 4.5 billion years. It can wait a few more decades for us to get our act together. And there's something almost philosophical about that. We are a civilization that has sent probes to Mercury and Venus and Mars and the asteroid belt and Jupiter and Saturn and Uranus and Neptune and Pluto and even beyond, into interstellar space. We have managed, through a combination of ingenuity, courage, and occasional luck, to extend the reach of human knowledge to the very edge of the solar system. But there are still gaps, still places we haven't looked, still objects we know exist but haven't studied. The map of the solar system is not yet complete. 1992 QB1 is one of the dots on that map that has never been filled in. It's the first object of its kind that we ever found. It gave its informal name to an entire class of objects. It helped prove that the solar system extended far beyond where we thought it did, in a structured and populated way that nobody had expected. And yet it has never been visited, never been examined up close, never been given the full attention of a dedicated spacecraft with instruments designed specifically to unlock its secrets. That's not a failure. It's a measure of how vast the solar system is and how early we still are in the process of exploring it. Every generation of space scientists has had to make choices about where to send the limited number of missions that budget and physics allow. Previous generations chose the planets, the moons, the comets, and ultimately the first Kuiper belt object that anyone had heard of. Future generations will have different choices to make, different priorities, different tools, different windows into the distant dark. When a probe does eventually go to the Kuiper belt with enough precision and capability to study objects like 1992 QB1 in real detail, it will be building on a foundation that goes back to August 1992, to a telescope in Hawaii, to 2 scientists who refused to stop looking even when everyone else assumed there was nothing out there to find. And it will be building on the work of Voyager 2, which crossed the Kuiper belt without knowing it, sowing the seeds of scientific curiosity that are still flowering today. The story of 1992 QB1 is ultimately the story of how science works. You discover something, you realize it's more interesting and more complicated than you thought. You build better tools, you make plans, you argue about priorities, you wait for the right time, the right technology, the right window of opportunity, and then eventually, if you're patient and persistent and a little lucky, you go. We haven't gone yet, but the reasons are all very human, very understandable, and very temporary. The Kuiper belt is not going anywhere. Neither is 1992 QB1, and neither, for that matter, is our curiosity about it. The outer solar system holds some of the most scientifically valuable and least explored real estate in all of the territory we inhabit. It holds clues to how the solar system formed, how water got to Earth, how life's building blocks were distributed across the inner planets, and possibly how common or rare our own cosmic history might be compared to planetary systems around other stars. The Kuiper belt is a library of the solar system's past, and 1992 QB1 is one of the oldest, most undisturbed books in that library. One day, a spacecraft will make the long journey out there. It will take 15 or 20 years to arrive. It will fly past in a matter of hours, or perhaps, if we develop the technology to decelerate, it will actually settle into orbit and stay. Its cameras will capture the first close-up images of a cold, classical Kuiper belt object. Its spectrometers will read the chemical fingerprints frozen into the surface billions of years ago, and what it finds will almost certainly surprise us, because that's what always happens when we actually go somewhere and look. The universe is always stranger and richer than we imagined it would be from a distance. That future mission will trace its scientific lineage back to a moment in 1992 when a faint dot moved across a telescope image in Hawaii and 2 scientists realized they were looking at something that had never been seen before. It will trace its engineering lineage back to Voyager 2, which crossed the Kuiper belt before we knew the Kuiper belt existed, demonstrating that we could build machines capable of surviving in that extreme environment. And it will trace its cultural lineage back to every person who ever looked up at the night sky and wondered what was out there, past the bright familiar planets, in the dark quiet spaces beyond. We are still in the early chapters of this story. The Kuiper belt has been known as a populated region for barely 30 years. In the timescale of the solar system, that's less than a blink. In the timescale of human civilization, it's one generation. We are still learning to read the map. We are still building the tools we need to explore properly. We are still making the arguments, in scientific papers and conference halls and budget negotiations, for why this particular corner of the solar system deserves our attention. But the arguments are getting stronger, the tools are getting better, and the window of opportunity, even if it hasn't opened yet, is getting closer with every year that passes. 1992 QB1 is out there right now. It's about 44 astronomical units from the Sun. The light you're seeing right now, if you happen to be looking in exactly the right direction with exactly the right telescope, left that object about 6 hours ago. It's a frozen, dark, ancient world, sitting at the edge of the solar system, patient and silent, and full of information we haven't yet learned to read. And somewhere on Earth right now, there are scientists who are thinking about how to get there, planning trajectories, designing instruments, writing proposals, making the case that this place matters, that the first known Kuiper belt object deserves the attention of a dedicated mission, that the scientific value of visiting it is worth the years and the money and the engineering challenges that stand in the way. They haven't won that argument yet, but they haven't given up either. And that's exactly the kind of story that the history of space exploration has taught us to pay attention to, because the missions that eventually happen are almost always the ones that someone, somewhere, refused to stop believing in. The outer solar system is waiting, and we will get there.